Kubernetes. I am Dr. Rajiv Mishra, Professor, Department of Computer Science and Engineering at Indian Institute of Technology, Patna. Content of this lecture. In this lecture, we are going to introduce Kubernetes. Then we will see why is Kubernetes required, then components of Kubernetes, and finally deploying applications with Kubernetes. So, let us begin with the introduction to Kubernetes. So, Kubernetes is the Greek word for helmsman or a captain of a ship. Now, the symbol which is used is drawn from that wheel to drive the ship by the captain. So, Kubernetes is also known as K8s. So, K8s is an abbreviation which results from counting the 8 letters between K and S. This becomes K8s, Kubernetes. Now, Kubernetes was built by the Google based on the experience of running containers in the production cluster. Kubernetes is an open source container orchestration platform given by Google, and that was outsourced that was open sourced in 2014. So, what is container orchestration? When we say that Kubernetes is an open source container orchestration platform. So, container orchestration means that overall process of managing the life cycle of containers that usually run in a production environment requires a method that is called container orchestration. Now, the question is why this separate container orchestration is required to manage the life cycle of containers in a production environment. So, container orchestration is required due to the rise in microservice architecture and the use of containerization, which is increased tremendously in recent times. So, therefore, the large applications which are spanning across multiple containers need to be managed not manually, but automatically, and that management of a life cycle of a container is very much needed due to the large scale deployment, and therefore, container orchestration becomes an essential component which is very much needed. So, these containers, for example, may be deployed by an organization to host its applications such as web servers, email servers, business servers, which earlier used to host on virtual machines or a dedicated server. Now, therefore, the modern application development heavily favors microservice architecture, and due to this rise of microservice architecture, the use of containerization has increased tremendously. Now, this microservice are now being provided in a containerized form, since it becomes easy to develop, deploy, manage them independently. So, the containers provide greater benefit over hosting applications on virtual machines. Eventually, this results in a large scale applications to grow and span multiple containers deployed across multiple servers or the nodes. So, the operating them becomes so complex. So, to manage this complexity, orchestration is required, and therefore, this becomes the answer to the question why is container orchestration is required. Now, coming to more details about the Kubernetes is that Kubernetes takes this approach of clustering nodes and orchestrating containers on a cluster level. Therefore, Kubernetes, if you understand, is that not only it manages the physical infrastructure, that is the servers which are networked across, but also it manages the containers which are running on this particular cluster level. So, Kubernetes has to do both the tasks. So, container orchestration, to be more focusing on this aspect of Kubernetes, includes a range of functions, including not limited to provisioning, organizational primitives, scheduling, automated health checks, auto scaling, upgrade strategies, and service discovery. Let us understand these terms in more details. So, provisioning, that installing or upgrading the local operating system on a node or setting up the container runtime there. Organizational primitives such as labels in Kubernetes, querying the containers, grouping the containers, and so on. Scheduling of containers to run on the host, that is on the nodes of a cluster. Automated health checks is to determine if the container is alive and ready to serve the traffic and to relaunch it if necessary. Auto scaling, that is increasing or decreasing the number of containers based on utilization or a higher level metric. Upgrade strategies, providing rolling updates and rollback mechanisms. Service discovery, to determine which host is a scheduled container ended upon, usually including the DNS support. So, therefore, these are some of the aspects of container orchestration which Kubernetes is required to manage. Now, let us see the working of or understanding of Kubernetes is in more details. So, there in the figure shows the Kubernetes architecture which follows the master worker model. So, you can see set of the nodes are termed as master, and similarly on the right side the set of nodes, they are termed as the worker nodes. So, this becomes an architecture Kubernetes. So, Kubernetes, where the master known as the control plane here, so this is called control plane, and this master manages. So, this master is also known as the control plane which manages the worker nodes. Now, on the other hand, the containers are deployed and executed on the worker nodes. Here in the worker nodes, the containers are deployed. And executed in the container in the worker nodes. So, these nodes have the virtual machines on premise or on the cloud or on the physical servers. They have the virtual machines. Now, this Kubernetes cluster in this particular figure is a collection of the nodes that are divided into two groups. That is the master and the worker node. So, these are divided into two groups. So, therefore, it is the master node, and the other one is the worker nodes. Now, the master nodes will run the Kubernetes control plane, So, the master will run the Kubernetes control plane which control the cluster, while the worker node will run the application, and therefore, will represent the workload plane. The workload plane is also sometimes called a data plane. Now, the control plane is responsible for managing the state of the cluster here. In the production environment, the control plane may span across multiple nodes or even multiple data centers. The workload plane or a data plane contains the worker node that run in a containerized application workloads. The containerized application run in a pod. Now, Kubernetes pods. So, pods are the smallest deployable unit in Kubernetes. Pod is the smallest deployable units. They are the basic building blocks of Kubernetes application. So, the pod hosts one or more containers and provide the shared storage networking for those containers. So, you can see here the pod hosts the containers, and once it hosts the container, then it has to provide a shared storage across these containers and networking for these containers. Therefore, the pods represent the set of running containers in a cluster. That is, it becomes the running cluster. Therefore, the pods are created and managed by the Kubernetes control plane. Now, going to more detail about the Kubernetes control plane. Now, control plane consists of the number of core components. They are the API server, etcd, then scheduler, and the controller manager. Now, coming to this API server. So, API server is primary interface between the control plane and the rest of this particular cluster. Now, it exposes a RESTful API that allows the client to interact with the control plane and submit the request to manage the cluster. For example, kubectl is a command line interface that can be used to manage the Kubernetes cluster. It uses HTTP REST API to talk to the API server. Now, etcd, here it is a distributed key value store, that is a database. It is used by the API server and other components of the control plane to store and retrieve information about the cluster. It stores the cluster's persistent state, which includes object data. What are the Kubernetes objects? So, they are the entities to represent the state of the cluster. For example, they can describe what containerized applications are running on and on which nodes, the resources available to those applications, the policies around how those applications behave, such as restart policies, upgrades, fault tolerance. Now, coming to the scheduler. So, scheduler is responsible for scheduling pods onto the worker nodes, in the cluster. It uses the information about resource required by the pods and the available resources on the worker nodes to make the cluster, to make the container placement decisions. The controller manager is responsible for running controllers that manage the state of the cluster. In Kubernetes, controllers are the control loops that watch the state of the cluster and then make or request changes wherever needed. It is similar to the control loop like in robotics and automation, that is non-terminating loop that regulates the state of the system. Now, each controller tries to move the current state, the cluster state, closer to the desired state. So, controllers can also be created by the users, engineers using Kubernetes APIs. The core component of Kubernetes that run on worker nodes includes kubelets. So, here you can see kubelets. So, kubelet is a daemon and container kubelet and a container runtime and kubeproxy. There are three different components of Kubernetes that run on the worker node. So, we are talking about the worker node now of a Kubernetes cluster. So, coming to the first component, that is kubelet of a worker node. So, kubelet is a daemon that run on each worker node, and it is responsible for communicating with the control plane. It receives the instruction from the control plane about which pods to run on the nodes and ensure that the desired state of the pods are maintained. Then next is the container runtime of a worker node. So, container runtime runs the container on the worker nodes. It is responsible for pulling the container images from the registry, starting and stopping the containers and managing the containers resources. The next is kubeproxy in a worker node. So, kubeproxy is a network proxy that runs on each worker node, and it is responsible for routing traffic to the correct pod. It also provides load balancing for pods and ensures that traffic is distributed evenly across the pods. So, covering more details of a Kubernetes cluster. Now, regardless of the number of worker nodes in a Kubernetes cluster, they all become a single place to deploy the application using Kubernetes API. Hence, instead of deploying an application to a server or virtual machine, it deploy in a into a cluster instead. A very important component of a Kubernetes, which enables these nodes, which enables those nodes, worker nodes and master nodes, to talk to each other in a virtual network that spans all the nodes that are part of the cluster. In a simple words, a virtual network turns all the nodes inside of a cluster into one powerful machine that can be seen as the sum of all the resources of individual nodes. So, the Kubernetes API server exposes RESTful API. The client using the cluster and other Kubernetes component can create objects via API. So, API server has the following function: provides a consistent way of storing objects in etcd, perform validation of those objects so the client can't store improperly configured objects, provides an API to create, update, modify, delete resource. A Kubernetes resource is an endpoint in the Kubernetes API that stores a collection of objects of a certain kind. For example, the built-in pods resource type contains the collection of pod objects. Now, API server also performs authentication and authorization of requests that the client sends, and is responsible for admission control if the request is trying to create, modify or delete a resource. It should be noted that only component that talks to etcd is API server, that is shown. All the component read and write data to etcd indirectly through API server. Therefore, the etcd also implements the watch feature, which provides an event based interface for asynchronously monitoring the changes stored data in the form of the keys. Now, when a key changes, its watchers get notified. The API server component relies on this notification to monitor and move the current state of the etcd towards the desired state. In Kubernetes, controllers are components responsible for managing and maintaining a desired state for various resources. They help ensure that the current state of the system matches the desired state. Almost every Kubernetes object includes two nested objects fields that govern the object's configuration, the object specs and the object status. So, specs describe the desired state of the objects, the status describes the current state of the object supplied and updated by the Kubernetes system and its components. In Kubernetes, controllers are the components responsible for managing and maintaining the desired state for various resources. They help ensure that the current state of the system matches the desired state. A controller can track one or more Kubernetes resource type. Examples of some controllers such as replica set. Replica set controller ensures a specified number of replicas of the pod are running at all times. Deployment controller provide a declarative way to manage applications. They use replica sets under the hood, but offer additional features such as rolling updates. Rollback deployment are commonly used for managing application lifecycle changes. Stateful sets controller are used to manage stateful applications, providing guarantees that ordering and uniqueness of pods. They are useful for applications that require stable network identities and persistent storage. Namespace controller of a Kubernetes is a way to divide the cluster resources between multiple users, teams or projects. It provides a scope for the names, ensuring that the names of resources within a namespace are unique. The namespace controller is responsible for managing these namespaces within the Kubernetes cluster. A node controller. A node controller is one of the core component in the Kubernetes control plane, and its primary responsibility is to manage the life cycle of the nodes within the cluster. Service controller, that is the endpoint. The service controller is responsible for managing the life cycle of service resources in Kubernetes. Now, when you create or modify a service, the service controller ensures that the corresponding endpoints are created or updated. So, what are the services endpoint? Service. A Kubernetes service provides a stable IP address and the port for a set of pods, allowing other applications within or outside the cluster to access them. The service controller manages the creation and maintenance of the services endpoints. Resources in the Kubernetes represents a set of addresses corresponding to the pods backing a service. So, when a pod are created or modified, the service controller updates the endpoints to reflect the current state of a healthy pod addresses. Now, daemon set ensure that all of or some nodes run copy of the pods. They are often used for cluster level operations such as running a monitoring agent on every node, job or and cron jobs manage one or more pods to perform a particular a task and ensure completion. Cron jobs are similar, but allow you to run the job periodically based on the schedule. Scheduler is responsible for assigning pods to the nodes. Scheduler process works as follows. The scheduler watches for a newly created pods that have no nodes assigned. For every pod that the scheduler discovers, the scheduler becomes responsible for finding the best node for that pod to run on. The nodes that meet the scheduling requirement for the pod gets called feasible nodes. If none of the nodes are suitable, the pod remains unscheduled until the scheduler places it. Once it finds a feasible, it runs a set of functions to score the nodes, and the nodes with the highest score get selected. It then notifies the API server about the selected node. It is called the process binding. Now, coming to the workload plane or a data plane side, the kubelet, that is the daemon that runs on each worker node. It is responsible for communicating with the control plane. It talks to the API server and manages the application running on its node. It receives the instruction from the control plane about which pods to run on the node and ensure that the desired state of the pod is maintained. It reports the status of application in the node via API. The main function of kubelet services are register the node it is running on by creating the node resource in API server, continuously monitoring API server for the pod that got scheduled on that node, start the pod's containers by using configured container runtime, continuously monitor running containers and report their status, events and resource consumption to the API server, run the container liveness probes when the probes fails, and terminate the container when the pod gets deleted from the API server. The container runtime, which can be the Docker or any other runtime compatible with the containers, run application in a containers as instructed by kubelets. There are two categories of container runtimes. The lower level container runtimes, these focus on running the containers and setting up namespace and C groups for the containers. Higher level container runtimes, these focus on the formats, unpacking, management, sharing of images and providing APIs for developers. Container runtime can perform tasks such as pulling the required container image from an image registry. If it is not available locally, prepare a container mount point, alert the kernel to assign some resource limits like CPU or the memory limit, pass system call to the container to start the container. Now, Kubernetes service proxy load balances the network traffic between applications. The service proxy runs on the nodes and ensures that one pod can talk to the another pod. One node can talk to another node and container can talk to another container. It is responsible for watching the API server for changes on the service and pod definitions to maintain the entire network configuration up to date. Now, when a service gets backed by more than one pod, the proxy performs load balancing across the pods. Now, let us take this Kubernetes components from the viewpoint of an application deployment. Now, setup includes, suppose we have an application that requires multiple containers, each hosting a microservice, although we can run all the application container inside a single pod. It may be prone to the node failure since the pod runs on a single. So, instead we can group applications to run on a separate pods that can be spread across multiple nodes. In this case, the pod must be able to communicate with each other as per the requirement of the application to facilitate communication between the pods. Kubernetes offer cluster network which assigns IP address to each pod. Cluster network is a set of links that facilitate communication within the cluster. Note that this IP address is assigned to each pod and not to the container. Each pod can communicate with the other using this IP address, which is an internal IP address. However, pods are ephemeral, which means that they can die very easily. For example, application or microservice running inside the container might crash, and when that happens, the pod will die and the new one will be created in its place. Consequently, it will be assigned a new IP address which may become inconvenient for our applications or directly using IP address to communicate. To address this issue, another component of Kubernetes called a service is used. So, the service API is an abstraction to expose the groups of pods over the network. Each service object defines a logical set of endpoints along with a policy about how to make those pods accessible. For example, consider a stateless image processing backend which is running with 3 replicas. Those replicas are fungible, that is front end do not care which backends they use, while the actual parts that compose the backend set may change. The front end client should not need to be aware of that, nor should they need to keep track of the set of backends themselves. So, the service abstraction enables this decoupling. It should be noted that the life cycle of the service and the pods are not connected. This means that the service will stay the same even when the pods die. So, the pods communicate with each other using the service. So, config map is an API object used to store non-confidential data in key value pairs. Pods can consume config maps as environment variable, command line arguments, or as configuration files stored in volume, that is data storage. A config map allows to decouple environment specific configuration from container images so that your applications are easily portable. For example, we can specify the same application to run with a different command line or arguments in different containers or the pods. So, a secret is an object that contains a small amount of sensitive data such as password, token, key. Such information might otherwise be put in a pod specification or in a container image. Using a secret means that you do not need to include a confidential data in your application code. Now, because secrets can be created independently of the pods that use them, there is less risk of secret being exposed during the workflow of creating, viewing and editing pods. Secrets are similar to the config maps, but are specifically intended to hold confidential data. Now, secrets can be used for various purposes such as the following: setting up environment variable for container, providing credentials such as SSH, keys or passwords to the pods, allow the kubelet to pull container images from private registries using login credentials. Persistent data storage in Kubernetes. So, Kubernetes provides volumes to persist the data generated by containers to permanent storage. By default, containers have no way to store the data persistently, since all the data associated with the container is removed when the container stops running. So, volumes abstracts an external storage and presents it to the containers running inside the pod so that the data can be permanently stored. Replication. Now, Kubernetes allows the pods to be replicated. This is useful for 2 major reasons: availability, that is fault tolerance, in case the node on a cluster fails. The second is due to the load balancing. It splits the workload across multiple replicas of the same applications. Now, here the service is common to all the replicas of a pod, that is to say that replicated pods have the same network address. Usually, the deployment process of an application requires creating a deployment configuration called deployment in the Kubernetes. Given that an application may be composed of multiple pods, the replication factor, that is the number of replicas, is usually defined for the set of pods that the application uses. The replication factor can be defined in the deployment configuration. So, deployment in the Kubernetes also allows for scaling of applications as well. Some pods are stateful, for example, database application container. In such a case, we cannot use the deployment, instead we should use stateful set. Stateful set in the Kubernetes manages the deployment and scaling of the set of pods and provides guarantees about the ordering and uniqueness of these pods. Like deployment, a stateful set manages pods that are based on identical specs. Unlike deployment, a stateful set maintains a sticky identity for each of its pods. These pods are created from same spec, but are not interchangeable. That is, each pod has a persistent identifier that it maintains across any scheduling. Stateful sets are useful for the application that require one or more of the following: stable, that is unique network identifiers; stable, that is persistent storage; ordered, that is graceful deployment and scaling. Ordered means automated rolling updates. So, the concepts discussed so far, we can deploy the applications on a Kubernetes cluster. So, the power of Kubernetes to deploy the software on the edge devices. Now, with a general overview of components that make Kubernetes, we can understand how to deploy an application in the Kubernetes. An application consists of several of the objects. One type represents the application deployment as a whole, another represents a running instance of your application, another represents the service provided by the set of these instances and allow reaching them at a single IP addresses, and there are many others. These objects are usually defined in one or more manifest files in either YAML or JSON format. So, these actions take place when we deploy an application on a Kubernetes cluster, submits the application manifest to the Kubernetes API. The API server writes the objects defined in the manifest to the etcd, and the controller notices the newly created objects and creates several new objects, one for each application instance. The scheduler assigns a node to each instance. Fourth step is the Kubernetes notices that an instance is assigned to the kubelets nodes. It runs an application instance via the container runtime. The kube proxy notices that the application instance is ready to accept the connection from the client and configures the load balancer for them. The kubelets and the controllers monitor the system and keep application running. For example, in the figure you can see deploying an application in the IoT cloud edge system. So, the architecture diagram shows the workflow from the cloud through the virtual kubelet through the edge provider down to all of the edge devices. First, the virtual kubelet project lets you create a virtual node in your Kubernetes cluster. A virtual node is not a VM like most other nodes in the Kubernetes cluster. Instead, it is an abstraction of a Kubernetes node that is provided by virtual kubelet. Backing it is an IoT hub. It can schedule workloads to it and treat it like any other Kubernetes nodes. So, when the workloads are scheduled to this virtual node, the edge provider comes in as depicted. So, the edge connector and edge provider, which are working in tandem with the virtual kubelet, it takes the workload specification that comes from the Kubernetes and converts it into an IoT edge deployment. Then IoT edge deployment is shipped back to the backing IoT hub for its virtual node. Lastly, the IoT hub in turn pushes this deployment down to all the targeted devices. So, let us see the benefits of using Kubernetes. The benefits of Kubernetes that you have learned, why many organizations across the world have welcomed Kubernetes into their data center. Now, let us take a closer look at specific benefits it brings to both the development and IT operation team. First is called self-service deployment of an application. Because Kubernetes presents all its worker nodes as a single deployment surface, it no longer matters which node you deploy your application to. This means that the developers can now deploy application on their own, even if they don't know anything about the number of nodes or the characteristics of each node. In the past, the system administrator were the one who decided where each application should be placed. This task is now left to the Kubernetes. This allows a developer to deploy the application without having to rely on other people to do so. When developer deploy an application, Kubernetes chooses the best node on which to run the application based on the resource requirement of the application and the resources available in the each node. Second benefit is reducing the cost via better infrastructure utilization. So, if you do not care which node your application lands on, it also means that it can be moved to any other node at any time without you having to worry about it. Kubernetes may need to do this to make the room for the larger application that someone wants to deploy. This ability to move the application allows the applications to be packed tightly together, so the resources of the node can be utilized in a best possible way. Next benefit is automatically adjusting to the changing load. Now, using Kubernetes to manage your deployed applications also means that the operations team does not have to constantly monitor the load of each application to respond to the sudden load peaks. Kubernetes takes care of this also. It can monitor the resource consumed by each application and other metrics and adjust the number of running instances of each applications to cope with increased load and resource usage. Now, when you run Kubernetes on the cloud infrastructure, it can even increase the size of your cluster by provisioning additional nodes through the cloud providers API. This way, you never run out of the space to run additional instances of your applications. Next benefit is keeping applications running smoothly. Kubernetes also makes every effort to ensure that your applications run smoothly. If your applications crashes, Kubernetes will restart automatically. So, even if you have a broken application that runs out of the memory after running for more than a few hours, Kubernetes will ensure that your application continues to provide the service to its user by automatically restarting it. In this case, Kubernetes is a self-healing system in that it deals with the software errors like one just described, but it also handles hardware failures. As the clusters grow in size, the frequency of the node failure also increases. For example, in a cluster with 100 nodes and a MTBF, that is mean time between failure of 100 days for each node, you can expect one node to fail every day. Now, when a node fails, Kubernetes automatically moves the application to the remaining healthy nodes. The operation teams no longer need to be manually moving the applications and can instead focus on repairing the node itself and returning it to the pool of the available hardware resources. Now, if your infrastructure has enough free resources to allow the normal system operation without the failed nodes, the operation teams does not even have to react immediately to the failure if it occurs in the middle of the night. No one from the operation team even has to wake up. They can sleep peacefully and deal with the failed node during the regular working hours. Now, finally, the last benefit is simplifying application development. The improvement described in this way mainly concern application deployment, but what about the process of application development? Does the Kubernetes bring anything to their table? It definitely does. As mentioned previously, Kubernetes offers infrastructure related services that would otherwise have to be implemented in your application. This includes discovery of services and or peers in a distributed application, leader election, centralized application configuration and others. Kubernetes provides this while keeping the application Kubernetes agnostic, but when required, the applications can also query Kubernetes API to obtain detailed information about their environment. They can also use the API to change the environment. Conclusion: in this lecture, we discussed about the overview of Kubernetes, a container orchestration tool, the need for using the Kubernetes and its benefits, component of the Kubernetes, control plane and the worker nodes, deployment of the application using the Kubernetes. Thank you.